So, more or less we discussed all the basic concepts in fluorescence, right. The origin of fluorescence, Stokes shift or redshift that happens. The spectrophlorimeter we discussed, what is the design, what are the principles. Some of the application we discussed, the steady state fluorescence and and also you can do some dynamics. Also we discussed the quenching phenomena, and we also discussed how you can use quenching to understand the location of your probe, which is fluorophore. So, those are some of the concepts that we discussed, but today onwards I am going to discuss some interesting advanced topic in fluorescence. It is not very advanced, but still it is advanced than whatever the practical application that you do in your MSc lab, but certainly these kind of concepts are used in research, also in the industry. So, all of these concepts that we are going to discuss today, and one of the starting point today is going to be inner filter effect, but before going to inner filter effect, let us do a little bit of recap so that we bring you to the same point. So, emission of light by a substance after absorbing the light or radiation, this is the fluorescence. Emitted light typically have a longer wavelength, which we call longer wavelength means lower energy, and that we call it the Stokes shift. Fluorescence differs from the phosphorescence, it has a longer lifetime, it is a slower process, right. It is coming from triplet state, fluorescence coming from singlet state. Now, some of the example that we have already seen quite a few of fluorescent dye, the biological fluorophore. Can you name a biological fluorophore? Luciferase. Green fluorescent protein we have already discussed, like green fluorescent protein. So, those are biological fluorophore. So, concept is molecule absorbs the light, goes to excited state, emits the light while returning to the ground state, that is the fluorescence, and emitted light has a longer wavelength, that is called Stokes shift. It is represented very nicely in a conceptual form from this diagram that we call it Jablonski diagram. So, Jablonski diagram is an excellent way of representing it. Then we discuss about fluorimetry. It measures the intensity on the y axis versus wavelength on the x axis, right. So, we measure the distribution, wavelength distribution of fluorescence that is emitted by. So, if you plot excitation, it will be called excitation experiment, intensity versus the wavelength. First you do excitation and then you have a emission. This that helps in understanding these two experiment, helps in understanding the molecular structure, because fluorophore has intrinsic property. The concentration one can measure, the environment you can measure, what is in which environment this fluorophore is. Now, you need to have a source, excitation monochromator, the sample cell, nice sample cell where only sample absorbs, emission monochromator, detector, and then you plot it in a data system. So, computer attached to that, right. So, these are some of the concepts on designing the fluorescence based assay. Study we discussed in detail, solvent has a effect, environment has a effect, right. So, solvatochromic effect, that solvent can change the band gap between emission and excitation, and we have seen that how it shifts the spectrum. So, solvent has profound effect on the fluorescence spectrum, and basically solvent can change, and that is one of the critical or crucial parameter when you are designing a sensor or detection probe or something like that, to look at these important aspects, right. So, today we will be touching upon a new topic called inner filter effect. Inner filter effect, how it works in a fluorescence spectroscopy. So, this concept of inner filter effect is quite helpful in something called sensing, right. Sensor we already discussed how fluorescence can be used in a sensing. So, inner filter effect based sensing, inner filter correction you have to do. Many times you do the experiment and this guy is contributing you where you are probably unaware, then your interpretation can be very different than whatever it should be. So, you have to do correction, and how inner filter induces the redshift, that we can use as a tool to understand or detect something. So, let us understand what is inner filter effect, right. What name suggests, कुछ अंदर ही हो रहा है, inner filter and some effect is happening. So, it is a phenomena in fluorescence spectroscopy where the major fluorescence intensity is reduced, right. There are so many already we discussed that is contributing towards this reduction, one more has come, and this phenomena is called inner filter. So, it changes the fluorescence emission or absorption, and this is happening because absorption of excitation or emitted light by sample itself, right. So, if sample is absorbing itself, what property it has? Bhasmasur kind of property, right, is not it? So, it is absorbing itself, it is destroying the efficiency of a fluorophore by self absorption. कैसे हो सकता है? Think little bit conceptually, कैसे हो सकता है? That is why I gave you this term. How it can happen? लिखा है, but we will come to that whatever is written. But think logically, why a fluorophore will reduce its emission or excitation by self absorbing. What comes to your mind? What could be? Intermolecular interaction, very good. What else? Intermolecular interaction means like it starts absorbing the self because of something. If your excitation is this and emission is this, right. So, whatever excitation and emission is matching, those kind of probability in a sample can start changing the whatever effective emission property that we have. These are called inner filter effect. So, let us delineate this step by step. So, if your sample is highly concentrated, it is a highly concentrated, the excitation beam is attenuated, because excitation what you want, my molecule is sitting here and whatever we put the photons for excitation, it should absorb and take it to the excited state. But suppose you are putting too thick sample. So, before reaching to the effective fluorophore, it is already getting disturbed by scattering, by transmission, by something, it is not reaching effectively, concentration is high, right. So, the like in those case the excitation beam is attenuated by the sample and only surface facing the excitation beam flows strongly. So, here is my cuvette, here is my cuvette and it is very thick, right, you can see it. I do not know what color her other pen is, I can only see this color, right, you can also see this color, but if I remove all of the pen, I have only 2 pen, you can see the color of the pen. It is a simple like that. If concentrated sample, what happens, wherever the excitation light shines, this gives good fluorescence, but when it comes to the other fluorophore, it gets attenuated, right. So, center of cuvette which is imaged by the emission monochromator of the fluorescence spectrometer has a lower fluorescence, because light did not reach here. She has a very colorful pen, I can see from top, but I cannot see from here, you cannot also see it, right. She has a very colorful fluorescent pen, right, I can show you here, it is a very colorful like this one, but it was just residing here, light is not reaching here, you cannot see it, same like inner filter effect. Even if it has a capability to absorb, but since it is too concentrated, light is not able to reach effectively, but my detector is only detecting here, right. My detector, which is my light, is tuned to look at here, but light is not reaching, right. So, this is called inner filter effect. So, it results in a spectral distortion in some cases because loss of the signal, and so user must learn how to prevent some of these effects if you are designing your experiment. So, what is the easy way to do that? So, you see this curve says if I am exciting here, my emission is sitting here, it is a good one, here light is going and you are detecting, but suppose it is a too thick and some light is getting transmitted, absorbed here, it is a distorted spectrum, and if it is very thick, light पहुँच ही नहीं रहा है जहाँ पर fluorophore बैठा है, you cannot see anything, that is a completely gone. So, no signal comes from there, that is a inner filter effect. So, what is kind of inner filter effect? You got the concept basically, right, got the concept what is inner filter effect. So, inner filter effect, how it can come? One, already I said concentrated sample has a problem, light is not reaching there, you are not getting enough signal from the molecule that is fluorophore sitting there, right. So, it can happen because of two effects, something called primary inner filter effect and second is called secondary inner filter effect. Let us see what is primary and secondary. So, occurs when a fluorophore or other chromophore in the solution absorbs the excitational light before it reaches the center of the sample. And it is also possible that in like here is my, again I will take her pouch. So, here is my fluorophore and my fluorophore of interest is her beautiful colored pen that is sitting in the center, right. Now, it is possible that when I shine the light, other molecules, other chromophore is there which is taking the light away. Now, it is not reaching effectively or not reaching at all. So, the signal is not coming, that is called primary flow. So, this leads to decrease in amount of light that can reach and excite the fluorophore of my interest, results in a lower emission intensity. If say only 10% light reaches here, 10% excitation is happening, and it is more pronounced in case of concentrated solution, that is a primary one. Now, that is coming in the path of excitation, whatever comes in a path of excitation wavelength, that is called primary inner filter effect. Now, look at what is coming in the path of emission spectrum. So, it occurs when emitted fluorescence is reabsorbed by another molecule, right. So, it is this, we shine it, somehow light reaches here on her that beautiful pink or purple pen, and this giving fluorescence, but whatever it was giving, there is another molecule to absorb it. So, now photon is not reaching to detector, enough photon is not reaching to detector. So, then whatever we measure will be quite reduced compared to what it should give, and that is called secondary inner filter effect. So, this leads to a spectral distortion, and because now energy has decreased, so it will be red shifted in the emission spectrum, and this again can happen because of light concentration. Now, that can happen, it is a phenomena that can happen. So, first is how to do it correctly, how you can correct it, and second will, if it is there, you cannot avoid how you can use it, that is the concept. So, strategy to mitigate or correct the inner filter effect, this happens, right. This is a part of, अब तुम ये नहीं बोलोगे कि नहीं नहीं मैं तो हरदम 10 माइक्रोमोलर को 2 माइक्रोमोलर डाइल्यूट करके ही एक्सपेरिमेंट करूँगा. Many times your experiment does not allow it, right. Suppose I want you to do in 100 micromolar sample and you say sir कुछ तो light नहीं आ रहा है, can I dilute it? You can dilute it, but you are not getting the correct information which should come from your sample. So, many times you are bound by the experimental design or correct way of doing. So, let us see how we can correct the inner filter effect. So, to manage the inner filter effect we can employ several strategy, something we can do with the instrument और एक्सपेरिमेंटल डिजाइन. तो एक इजी वे है सैंपल डाइल्यूट कर लेते हैं अगर अलाउड है तो. वी कैन डाइल्यूट द सैंपल राइट एंड देन वी कैन have the, so you dilute the sample and see absorption is reaching with dilution, right, because light has to. So, first you check it by diluting sample, and if it is increasing the absorption, that means now excitation should happen effectively, and then it should not happen that dilution should not change the chemical property, right, that is the catch you have to have. Alternate strategy is you need to have some design change in the fluorimeter, right. So, it can have a front face fluorescence. In this configuration both excitation and emission are measured from the same side of the sample, right. You look at what we are doing here, we are putting excitation like this, emission like this, right. So, like this it is not going and whatever comes. So, if I put emission also here, it goes and comes back, I can detect it, or not exactly like this. So, something on this angle. If I put the mirror, it can do it. So, that is a design change in the spectrophlorimeter. We can put it at 0 degree or 45 degree to the excitation. This minimizes the path length through sample and better suited for highly concentrated or opaque sample that we have for experiment. We can have another cuvette का size घटा देते हैं. 1 mm it has to travel a lot, but if I have 0.1 mm, sorry 0.1 cm, 1 cm is this thick, 10 cm if I reduce to 1 mm, the path length is reduced and light does not have to travel that much. So, you can have a shorter path length cuvette, we can have 1 mm instead of 1 cm, can significantly lower the effective absorbance. Now, cuvette selection is extremely important parameter for doing it, right. If you go to any fluorimeter lab, you have a different size of cuvette, mota, patla, whatever. So, if your quantum yield is less, you cannot do with like that 1 mm, because you need to have enough light absorbed by the enough molecule in the cuvette. So, that is why the companies make a different size of cuvette. It is a thicker, thinner, whatever. So, but because of inner filter effect, if your concentration is high, you can afford to dilute it or reduce the path length, so that it gives you effectively the signal. And you can readjust the optics, you cannot have a fixed one if it is not coming. As I said, 0 degree or 45 degree emission you can have. So, you can also change the position, कहाँ से तुम्हें fluorescence लेना है. So, Z position staging like a advanced fluorimeter that are there, but you can change the absorption and emission length if you want to take it from here. So, that is Z position of optics. You can have a effective path length change, and that is called inner filter correction method by ZINFE method for correcting it. That is experimental design how you can do it, changing the path length, diluting the sample, changing the optics. 3 way you can correct the inner filter effect. Now, something in calculation, like theoretical framework and mathematical correction also you can employ. You are knowing where is the problem, right. So, one is engineering solution, one is a scientist solution experimental, some is data collection, data processing collection. So, inner filter effect happening because of non-linear relationship that is happening between fluorescence intensity and concentration, right. Here not all the molecule effectively giving you fluorescence. That means if you increase the concentration, the fluorescence is not going like this, but it is saturating like this and coming. So, one can have a standard correction equation where you have a optical density, you have to keep below 0.3, and then absorbed fluorescence is corrected for using this formula. So, F correction will be F absorbed divided by excitation absorbance and emission absorbance, that value divided by 2. So, this is one of the way you can correct it, the inner filter effect. Another one, like there are modified model that has came, it's recently came. So, introduce the correction in equation by incorporating the emission angles, right. I said that you can adjust this, so emission angle you can do it, and that improves the accuracy of that. The third one also we discussed, G positioning, one can do it, and that allows to separate the signal coming from the measurement. So, doing this you can put it in the correction and find it the instrumental mathematical correction model. Instrument adjustment if not possible, then mathematical correction can be applied to the raw data, typically requires independent measurement of sample absorption at both emission and excitation wavelength. Change it little bit, see at what wavelength it is giving what, and then you can correct it mathematically. The widely used is Karl-Lakowicz method, right. It is a correction formula that assumes fluorescence is collected from the center. I was saying what is the problem here for inner filter effect? It is not collected from the center, it is coming. So, in this methods you have to assume that it is whatever is correcting. So, that is a way of doing it. Then a new method came, it is called Parker-Holland method. It incorporates the specific geometry parameter of the instrument observation field, the cuvette where it is, and then measures at the higher correction. So, these are some of the way probably you can do it the correction. Now, extremely important the geometry that we use. So, typically what geometry we have for cubed? Have you seen it? Square or rectangle shape, right? That is a typical way. It depends upon how you position. Okay. What is the slit width? If you do the experiment, you will learn it. Slit width का मतलब क्या होता है? Light कितना आया, right? How much channel you are opening? If you open too much, it saturates. If you open too little, there is no light coming. So, you have to be optimally adjust the slit width of the excitation and emission. These are experimental considerations that one has to do. Now, another important is sample geometry, right. So, what is the position? You can have this stage positioning in the cubed where we are putting it. Typically, you put it in the center. So, it critically affects the fluorescence, and why you want to keep it center? Here excitation, here emission. If you are not putting it correctly, the light is not going to the monochromator optics and then to the detector. So, geometry is extremely important. It critically affects the fluorescence intensity, and it can have effect of whatever we are talking about. If suppose your excitation is here and emission is sitting here, light is not going correctly. So, this optics adjustment is extremely important, and how it is done? Angle change करते हैं, but who does it? The engineers who are coming. So, first what they do, they have some standard solution. They come and adjust the each parameter of the spectrophotometer. But when you are doing advanced experiment, many times you have to do it. So, you have to learn it. It is not just a tool where you go and get answer, you have to adjust that. So, geometry is extremely important, right. So, physical arrangement of sample, the excitation beam, the emission detector should be in a perpendicular direction for having effective one, right, 90 degree to each other. The preferred method to minimize inner filter effect. If it is not here, not like this, if it is somewhere shifted, you are going to have inner filter effect. Inner filter effect is in simple term reduction in the fluorescence intensity. So, inline geometry is extremely important, and that can be adjusted by doing the correction by someone who is more equipped, engineers and something, or in when you are going and doing the experiment in the lab, some person who is more expert like a senior PhD student or postdoc, they can adjust the optics to get the better fluorescence intensity by reducing it inner filter effect, or somebody who is who is very familiar with staging, the changing the slit width and all those. So, this is part of the experimental adjustable that you can do it. So, dilute the sample to low concentration where inner filter effect is minimal. Then you can use the numerical correction, the formula that I showed you here 2 slides back, something like this, and also you adjust the vertical position of optical elements. Sometimes you have to adjust the cubed to find it out, minimize that, right. So, what are the effect of sample geometry? As I mentioned, sample geometry is very important. Preferred one is 90 degree excitation and emission one, right. So, right angle geometry, if you have excitation enters to the sample and it is emission is directed at the 90 degree. So, that minimizes the scattering of excitation light, and sensitive to inner filter effect for concentrated sample. So, for concentrated sample, this is not a preferred one, diluted, this is a preferred one, right. Front face excitation and emission detected in the same angle, right, detected same side at an angle either like this or like 45 degree. That ideal for turbid opaque sample or a solid sample, and that lowers the intensity, but here the alignment is very critical. You cannot just do it as it is, you have to align the optics to have the minimum disturbance coming from there. Then it can be total deflection. So, excitation light reflects internally within the sample, that could be one of the issue, and you have to use the surface sensitive measurement, only you are measuring from the surface, not from the interior. Complex setup required, limited on a thin film. Suppose you are putting a thin film, material guys work on thin film or electronics work on thin film. So, here you are shining the light and getting it from here, right. So, that is a fluorescence you can say for materials application. Fiber optics probe, right. So, light is delivered through a fiber optics and portable fiber optics in situ measurement is required and lower resolution, but prone to background interference. Let us spend 1 minute fiber optics probe. Do you think where we are going to use such experiment? Fiber optics probe. Fiber optics all of you are aware क्या करता है? Huh?
Total internal reflection.
Very good. So, this is the concept. Can we use this for a complex sample to measure? Fiber optics approach. Suppose मुझे टिश्यू के अंदर कुछ देखना है. Tissue is thick, right? I am just keeping it biological. You can convert it to material as well. So, if I want to see inside a tissue what has happened and my fluorophore is sitting somewhere, it can be a GFP or something or a molecule, a drug molecule. Let us take a drug molecule, doxorubicin, red color का molecule है and sitting in a tissue sample. I want to see where this guy is sitting and what it is doing. So, I cannot take that tissue and put in a cuvette and जाके lab में experiment कर सकते हैं. We have to design some other experiment where we will shine the light using fiber optics. It is a thick sample, right, prone to all sorts of problems like inner filter effect or whatever, but still we can put it and do these experiments using fluorescence concept. It is a portable, flexible, because fiber optics is flexible. So, light I can take it and put it on the probe. Only problem that there will be background interference. So, sometimes you have to do the correction for background to get the signal from that, but good part is that concept can be utilized in understanding it, right. So, geometry is important, right angle geometry 90 degree as we discussed, front face geometry like a front illumination for thin film or something, you just shine it here and collect at a 45 degree emission, and also transmission geometry 180 degree. So, less common setup 180 degree means like a going like this and collecting like this, you less common, but opposite side of the sample you can have excitation source. So, these are some of the geometry for inner filter effect, right, where we use it, where we are going to use this inner filter. I said the problem. Now, let us use this problem for, it is a problem, right, inner filter effect is a problem because it is making our sensitive technique to less sensitive, right. So, political circle में इसको बोलते हैं आपदा को अवसर में बदलना. So, that is a, now let us put it this आपदा in अवसर, we can use it, right. So, the one use is sensing, right, you can use it for fluorescent sensing or biosensing. Now, modern assay for inner filter effect can be used as a turn on off and turn on mechanism, right, for sensing. You can detect the pesticide, detect the antibiotics, heavy metals, right. So, here as I was saying it is a concentrated sample is there and we can, if the molecule is present it will turn off, if molecule is not present it will turn off. So, if fluorescent signal is coming, you know that it is not there, or reduce is coming, it is there at low concentration. So, this kind of sensing one can use it. Inner filter effect based sensor, you do not require a covalent bond, like I will come to FET in few minutes or maybe hours. It is measuring the distance between two fluorescent probe, that is called fluorescence resonance energy transfer, but you have to tag it to the your biomolecule. In this case it is not, you do not need to tag, you just want to measure if present or not. You can use this inner filter effect based sensor to link the absorber and fluorophore and make them more flexible and straightforward in design. If the absorber is present and fluorophore is present in a proximity, you can turn on and turn off mechanism can be used for biosensing also. Second one, you can use it for environmental sensing, right, environmental sensing. Here in this department, it is environmental science, there are many people who works on wastewater treatment. Why it is important wastewater? treatment not, wastewater detection you have to also measure. Water is very, very important commodity that we are having, and we are making it more contaminant. Powai lake, can we just take a glass of water and drink it? No? Ganga ji? No? Brahmaputra? No? Why? What we have done with this? अच्छा चलो और थोड़ा ऊपर चलते हैं. मानसरोवर लेक, कैलाश पहुंच जाते हैं एक ही बार में. Can we take a water and drink it? So what is difference between Kailash water and Ganga ji water? Probably in between civilization we have made it dirty. In spite of Namami Gange project, Ganga is not clean. And who is responsible for it? We the people of India are responsible for it. हमने गंगा जिनको पूजा उनको दूषित कर दिया. और if something is in मानसरोवर, आदमी वहाँ नहीं पहुँचा, एक दो लोग पहुँच जाते हैं घूमते फिरते, it's still clean and you can drink the water from Mansarovar lake. Probably I have never been to, so I really don't know, but I assume that. So environmental sensing is has become extremely important nowadays, because you know that there are pollutants present in the water. Even normal water, wastewater to chhod do, natural water, and because organic constituent has come, use of pesticide, use of whatever fertilizers, soap use, right? All of us wants to use L'Oreal to become Gora, whatever, Kala, whatever, but it's putting lots of organic molecule in the water and it is making it polluted. Now when we want to do any use of those water, if you are not using, then it's a problem, because water is constant, right? It's a recycling, and it is becoming pollutant. So if you go to Punjab, Ludhiana, what is the problem with Ludhiana water? Polluted, coming into food chain, क्योंकि वहीं वाटर क्रॉप में जाता है, क्रॉप वहीं दूषित वाटर पीता है, और जो ग्रेन बना that's containing all of these. So water is becoming problem. So now one way to do the, first of all, it's a problem exists. As a scientist, what is our job is to find a solution, probably first detect it, where is the problem, and then come up with a solution. So we can use like a dissolved organic matter detection based on the fluorescence, wastewater or natural water. These organic constituents absorbs heavily in the UV. So you can have your fluorophore, and if water is cleaner, your signal will come more. If water is polluted, have this organic constituents, it will be inner filter effect will take the absorption and it will come. So you have a reduced light penetration, reduced emission because of all these pollutants that you may have. That's a use in environmental. I was already talking about Ludhiana problem in food. Food is also problem, food is contaminated, right. So you can use this ratiometric fluorescence platform to use inner filter effect to monitor the residue in food sample, right. So if there is something is present in the milk, in the pork, in grain, wherever it is, you can detect it, right. All of us require doodh, milk, right. From morning tea to late evening golden milk, if you want to drink it, you can drink. And being the country where the milk is one of the important ingredient of our food, from the birth of the kid to the death of a person, milk is important part. Milk is one of the most contaminated food that we have, right. अब किसी के घर में गाय तो है नहीं, मैं बचपन में था, मेरे घर में गाय थी, दादाजी दूध के दे देते थे एक ग्लास. ना सब तो पॉलीथीन के पॉकेट में आता हुआ दूध पीते हैं, right. All of us are drinking the same milk. How do you know that milk is not polluted? It's heavily problematic. Now I cannot take my fluorimeter and go a village in Mehsana district in Gujarat and detect it. I am just telling the name of Mehsana because last week I was there. So you cannot do that. So what you can do? Make a portable fluorimeter where you can detect the purity of a milk which is coming to the dairy, and from there it is getting transported to Mumbai where we are consuming it. So these kind of food detection of a milk, of any green or anything that we can think of, a simple absorption emission based portable fluorimeter can be made, which can possibly detect the adulteration that is happening in the food. Right. The last one, material science. Right. So, material science, the fluorescence based experiment for characterizing the quantum dots or metal organic framework. Quantum dots, all of you have, it is a now sensor based things are happening because of quantum dots advancement. A MOF, how many of you have heard about MOF? Metal organic framework. It is one of the important material which is coming metal and then carbon bond bana ke packaging mein, delivery mein we are using MOF. So, this actually helps in precise knowledge of emission property, and that you can use in display, the lighting or whatever, sensing and delivery and all those. So, it has a important concept, this inner filter effect, although it is a problematic, but you can use this concept in detection, in sensing and many other. So, what we can conclude, the inner filter effect can significantly affect the fluorescence emission and distort their like a shape, it can shift the spectrum, maxima can change, the emission wavelength can change. Now, if this effect is influenced by the geometry from where sample the signal is coming from, and excitation volume and detection volume can be also contributor to that. Two kind of inner filter effect that we looked at, primary and secondary. The inner filter effect can be a problem when loss of intensity varies between the measurement because of the all problem that we said, and then we can inner filter effect can rise from the attenuation of excitation and emission and sample is absorbed. Geometry plays a vital role that we discussed, and we can optimize it by putting the emission optics at a certain angle. We can mitigate the inner filter effect to work with a low concentration sample and also changing the optics, and there is some corrections that we already discussed with, that mathematically you can correct it and have the better way of inner filter effect. So, that was one concept that I wanted to discuss of inner filter effect.